also screen sharing. I keep forgetting that, and I thought all of you were looking at the screen already, and I go like, no, okay, maybe I forgot. There we go. Okay, now you guys can see it. So there were, I think there were some interesting traffic in the off-topic channel, about this strange programming language that I cannot, say out loud in a recording. But that really is the name of the programming language. Okay, I did not make it up, and Wikipedia also did not make it up. But that's basically a thought exercise. I mean, that's basically a thought exercise intended for people who just kind of want to bring take on some additional challenges. And I also talked about, I just released it today, but I have been working on that writing for some time. But my qualifying exam, to become a candidate for the doctoral program, also had interesting questions in the programming language, department. And some of you may say, but you were a graduate student already. You're supposed to be able to answer those questions. And I can tell you, nothing from graduate school or graduate courses can actually prepare you for those questions. I mean, it really is. Nothing in graduate school helps with that type of question. If anything, by the time you get to graduate school, you're older. Your brain doesn't function as quickly anymore. So it's actually a disadvantage to encounter those questions in graduate school. Anyway, all right. So I think it's time to get started. So we are now looking at the exam from last semester. This is the final exam from last semester. There were 4 questions last semester. Sometimes I give 3 and sometimes I give 4. And the first question is about probability. So we'll go ahead and start with this one. So I'll read the question. Let me zoom in a little bit because it's too small and it doesn't need to be that small. There we go. So now we can actually read it, especially for those of you who are trying to watch the lecture from a mobile device or a cell phone. All right, so the length of a correctable data packet is 256 bits, and A is 256. It has been observed that the chances of having exactly 1 bit of error is B, which is 0.307 and blah 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 blah. Solve for the per bit error rate C, and be sure to include an explanation of the rationale of how you formulate the equation. If you do not have a calculator that can solve this, okay. I thought my computer was just freezing up and dying. It turned out it was just the screensaver. If you do not have a calculator that can solve this equation, you can just leave it unresolved without any penalty of points. Okay. Unrelated. Okay, so I'm getting some other notifications from other servers on Discord, so I had to take a look. Using C, compute the chances of a packet having too many error bits for the self-correction mechanism. Assume that the self-correction mechanism can self-correct for up to 3 bits. All right, so now that we have read the question, now we want to figure out, okay, so what does it map to? Okay, because every single question has to map to things that we have learned already. So it is a matter of understanding what the question is asking, and then mapping it to one of the things that or one or more of the things that we have talked about in class. All right, so the first thing is we do know that each data packet has 256 bits, okay? So right away, okay, in your head, okay, what is a bit? Okay, a bit is a binary digit, which means it's either a 1 or a 0, okay? So the question now is, okay, how does it map to things that we have learned already? Well, for one thing, we know it is with replacement, right? Because once you have a 1 appearing in a packet, can it reappear somewhere else in the same packet? The answer is yes, okay? So it is with replacement. And once it is with replacement, the next question is how many possible outcomes do we have per event? What is not event? Let me take it back. Trial. That's it. So how many possible outcomes do we have per trial, and what is considered a trial? Okay, so those are the questions that we need to ask, or at least start to think about. And then the next sentence says it has been observed. So this is based on observation that the chances of having exactly one bit of error is b equals to blah 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 blah. Okay, so now we have to ask the question: what exactly do we mean by one bit of error? So the one bit of error is one bit of error per packet. So if you're not sure about that, okay, you can certainly ask for clarification, because that is a part of what you need to understand about the question, and I would certainly answer that particular question about clarification. So this one bit of error is per packet, okay, and one packet has 256 bits. So the next one is to solve for the per bit error rate C. So you can see how the confusion may pop up. Basically we have one bit of error is B, and then next we ask about what is a per bit error rate. All right, so someone it doesn't have a percentage symbol, so that is just so it's equivalent to 30.72% or something like that. It doesn't have a percentage in it, so it is not a percentage. It is just a ratio, which is pretty high, don't you think? So does it mean probability of having one bit error every for each packet? So let me just kind of add this. So I'm gonna use a different color so that you guys can see what I just added here. Or I can go for there's a way I can do this where it automatically highlights it, but you guys won't be able to see it, so that won't be effective. Never mind. I'm going to change the color, and I'm going to use this blue color here. Okay, one bit of error. Oh, okay. And there really should be a per packet here. All right, so let me highlight it so that you guys can see what I mean by that. And highlight should be light color. There we go. All right, so this is one bit of error per packet, and that is B. So the first question is asking you about a per bit error rate. In other words, if I transmit just one single bit, okay, what are the chances that that particular bit is transmitted incorrectly or received incorrectly? All right. If you want to see this as a percentage, you can see it as 30.729676564 blah 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 percent. So you can see it as a percentage, but if you see it as a percentage, it would no longer be 0.3 something percent, it would be 30 something percent. So I hope that answers Elijah's question. And Nathan's question is yes. Okay, the answer to Nathan's question is yes, it is a per packet error rate of one single bit. Okay, so if you look at how often out of transmitting 256 bits, of which one and only one bit is incorrect, then the chance is 0.3072 blah blah blah. So there we go. So would we divide the per packet error probability by 256? Aha! Okay, so here is the tricky part, right? So the tricky part is, how do we figure out C? And let me read Danny's comment first. I have to be honest, if I got this question on the test, it would have taken me at least 20 minutes to even figure out what it's asking me to do. Well, well, if you have some idea of what it's asking, but you're not quite sure what a term is referring to, like what is this term one bit of error is referring to, you can always ask for clarification. And I can also tell you, the question, it was not intentionally difficult to understand. It's just that I forgot to mention the per packet here, because in my mind it was in the per packet data packet context, so it did not occur to me that the question in the first question would have caused some confusion here. Um, it is about mapping, right? So the idea of this question is, we are given a particular scenario, and we know that some of our tools that we have learned is used to solve this problem. So it is about mapping the problem. Ah, well, okay. So that's what I've been doing is try to describe, how we map the problem. Is we now understand, we have a with replacement type of trial because every single trial is the transmission of one bit. Okay, so every single transmission or reception of one bit is a single trial. So knowing that, we know that out of 256 trials, the chances of having one single error bit is this chance here. So the next question is, if we already know this is with replacement and each trial has two possible outcomes, does that remind you of a particular type of probability distribution? So that is the question, right? Exactly. So it is the coin flip issue. Okay, so basically we are looking at landing on the head as a bit being received correctly, and then landing on the tail is having the bit received incorrectly. Um, I mean, that's how you want to assign the head and the tail to erroneous versus not erroneous. It's up to you, but it's just that we have those two possible outcomes, and the probability of B, you cannot just divide it by 256 because of the binomial distribution. Okay, so you have to look at this problem and go like, okay, how does this number, what does it relate to in binomial distribution? All right, so that is basically what we need to try to figure out. All right, so now that we already know, okay, so I know making all of these connections may take some time, but now that we know, we have a problem where we have 256 trials. Each trial is with replacement, and each trial has two possible outcomes. And out of 256 flips, so to speak, the chances of having one and only one flip landing on the head is exactly 0.3072 blah blah blah. The question now is asking, what about if I just flip a coin exactly once? What would be the chances of having the coin to land on the head? So that's basically what the question is asking. All right, so I am going to use a note for today. So this way we can kind of look at it from a equation perspective. And I'll let you guys kind of think about this a little bit yourselves. You can write down your potential answer on a piece of paper. And then when we get back to, I have to search for, I have one server that's already running, so I have to close that one first, and I have no idea where I put it. Okay, let me look for that. Oh, there we go. Okay, so that's from my other class. There we go. Okay, so this is 0209. There we go. All right. All right, so what we are looking at here is we are looking at 256 trials with replacement, okay, and exactly 1 in 256 trials having an error. Oops. Error is whatever the number B is. So now what we need to do is to say, okay, what about the per trial probability of an error? So it is a binomial distribution because if you think about this as flipping a coin, in other words, we're flipping a coin 256 times, and of the 256 times of flipping a coin, getting exactly one head, okay, is B. Okay, so I know B is 0.30 something, but for the time being we just call it B. So the first part of the question is asking, so how do we figure out the per flip chance of landing on the head? In other words, how does B relate to the per flip chance of landing on the head? So in order to do this, okay, so I'm hoping you guys kind of recognize that this is a coin flip problem, which basically, the technical term is the binomial distribution. So in a binomial distribution, we have something. So if you go back and look at the binomial theorem, then you understand that we were looking at. Okay, let me just put it here. We were looking at something like p plus q, and okay, I got that, to raise to the power of some n, and that should equate to some sigma, some summation. I'm hoping you guys do remember this. So I goes from 0 going all the way to n, and then each term that we are adding within the sigma, within the summation, is going to be, okay, it's going to be n, choose I as one. Oh, that doesn't look good, does it? Let me see what I can do about this. Yeah, I see why. Okay, so we just have to put braces around this group, turn this into its own group. There we go. And then whether you want to use p, raised to the power of I, or q, it's symmetric. So I'm going to use p to raise to the power of I times q raised to the power of n minus I. All right. So this is how this is what we understand about the binomial distribution, because this is the binomial theorem. So the binomial theorem is looking at this, and obviously in this case, if you look at this from a certain perspective, this is pointless, because p and q, they both have to add up to exactly 1. So it doesn't matter what n is, we know this sigma is going to add up to 1. So that is not the interest. The interest is not on the sigma itself. The interest is on each term of the sigma. Okay, what is each term representing, right? That is the question. Okay, so do we have any questions about, or do you guys have any answer, I should say, about what each term is representing in this sigma notation? What is it representing? And how does it map to our question? Okay, so the way this maps to our question is we basically perform a particular experiment where it has exactly 256 trials. Okay, so that is the first thing that we need to set up, is to look at the binomial distribution and say, what is it? How does it map to this question now? All right, so we have p plus q, raised to the power of 256, and we know that there's a whole bunch of terms, of which there's one term specifically that we are interested in because of what b is representing. So what I'll do is I'm just gonna copy this over here. I think the dollar sign is repeated, which is not the way not how I intended it. All right, so this is 256, and this one is 256. The rest I can kind of leave it the same. Of all of these terms, which one is B? That becomes the question. So I'll give you this. Okay, P is the chances of having an error. Okay, so knowing that P is the chance of having a single error from the transmission of 1 bit. Okay, so knowing this, what is B? Yep. Okay, so B equals 2. And I'm going to give you the full formula, not, Marco is giving us kind of the, exactly. Okay, Dalton beat me to it, but I'm gonna put it in anyway. So it is going to be 256 because there are 256 bits being transmitted in a packet, but one of them, exactly one of them, is erroneous. Okay, so that's why we have a choose one. So that one is the one that has the chances of being erroneous. And then the rest, which is what Q is representing not transmitted erroneously. So Q is basically representing the 1 minus P, but at this point we'll just call it Q. It's raised to the power of 256 minus 1. Yes, I know that it's just 255, but I do want to present it this way because now we actually get to see where the 256 is coming from and where that 1 is coming from and how all of these things are related. So, very good. And now what we need to do is to look at this and in a very slightly way because we only want to solve for one particular probability. So we are just changing Q to basically what it really is 1 minus P. Now, to solve for this P is not going to be easy. I have to be honest. I have searched on the internet of how to solve for a variable, in a binomial equation like this. And as it turns out, if you have a smaller power, there are tools out there that can solve this. But when you have when you have the power being 256, or 255 in this case, there are no tools that I could find on the internet that can solve this. So you can leave it like this, because the question did say that if you do not find a tool to do this, or if your calculator cannot solve for this, you can just leave it as it is, just in this particular format, because we already know the value of this is basically 0.307 something. So so basically given the right tool, we can we can solve for the value of P. All right, so I'm gonna pause here and see if you guys have any questions. So when you see a question, that is clearly about probabilities, then you have to think, how does this question map to the different ways of computing probabilities that we have already learned. And there are only like it depends on whether you consider some are subtypes of others. Okay, so at the highest level, the first question is it with or without replacement? If it is without replacement, then we are going to consider either combination or permutation. If it is with replacement, then we have two subcategories where one is saying if each trial has exactly two outcomes, that would be the binomial distribution. And then the other one is doesn't have a name. It is with replacement, but it is not two outcomes per trial. So that one is just a power function that we have to apply. Oh, cool. Okay, so the TI-84 calculator can solve this, because I think it is empirically solving it. It's not solving it by symbolically. Am I correct about that? I mean, obviously you probably need to know how it's implemented, but I think it is only solved empirically, which you can also do with a spreadsheet. But in the question, I'm not even bothering to ask people to solve for it, just so that we understand how the problem should be approached. All right. So, any questions? Any? All right. So Dalton is typing. Oh, okay. All right. It sounds like it's empirical, because the non-empirical way to solve for this is really ugly. And this is certainly something that you can solve empirically too. All right. All right, the next part of the question can also be extremely confusing now that I look at this and go like, oh man, that's confusing. Because using C, that can also be interpreted as using the C programming language, which was not intended. Using C as the value that we figured out earlier. That's basically the C that we are referring to. So using the value C, compute the chances of a packet having too many error bits for the self-correcting mechanism. Assume the self-correcting mechanism can self-correct up to 3 bits. So that means if you have 0 bits of error, hey, you don't have a problem. If you have 1 bit, okay, of error per over the 256 bits, you do not have a problem. If you have 2 bits of error, not a problem. Up to 3 bits, okay, you still don't have a problem. But everything beyond that, if you have 4 bits, 5 bits, 6 bits, and so on, all the way up to 256 bits, every single bit was wrong, okay? Then we have a problem because we cannot self-correct for those cases. So how would you, solve for this particular probability in part 2 of this question? Now, it's only asking you, okay, I didn't quite say it specifically, but it really only needs to know the equation to do this, not so much the exact value. Because if the first part says, if you do not, give me the exact value, as long as you show me how to solve for it, it's going to be okay. So that means some people will not have an actual value for C, and without the actual value of C, you cannot have the exact value of part 2. You just have to set, show me how you would set it up. All right, so let me get back to the notes here, because the answer or the solution is closely related to the binomial distribution. Look at this sigma here. We know it's going to add up to 1, right? And we also know the chances of having 0 bits of error is part of this. The chances of having exactly 1 bit, which we know is 0.307 something, is also one part of this. And by extension, we know having 2 bits of error is part of this. Having 3 bits of error is also a part of this. But we are not interested, okay? The question is not asking about, what are the chances that the number of error bits is correctable. It is asking you about the opposite, right? It's asking you about the chances of what if we have so many error bits that we cannot correct for those error bits. But those two are complementary, okay? One is 1 minus the other one, because it is either this way or that way. So we have Elijah typing, so we have to find all the chances where the error is greater than 3, or you can find the chances of 0, the summation of 0, 1, 2, 3, and then say the rest is just 1 minus that. Okay, so both are correct answers, especially if you do not want to actually compute the value and just give me the form of an equation to solve for that. So I'm going to be super lazy here and just say that the chances of chances of too many error bits to correct is, so I'm going to get rid of the first part here. Okay, so get rid of this part, and I'll keep the summation. It's just that I'm not starting from 0. I'm going to start with too many, which is 4. Okay, and that's it. This is as lazy as I can possibly get. Okay, now the other way to answer this question is to say 1 minus, and this time you do want to change the summation from 0 to 3, because these are the ones where I can, there's enough information remaining in the packet for the self-correction. So if I do a 1 minus that becomes the chances of too many error bits for self-correction. All right, C is exactly, so Elijah is correct. C is the probability that 1 bit is transmitted incorrectly. Yes. So if I transmit 1 single bit, what are the chances that that 1 single bit is received incorrectly? So something went wrong in the transmission. Yep. There you go. Alright, so I'm going to give you guys a little bit of time to kind of look back into this question and see if you have any questions. In other words, what I use here as variable p, that really is C, uppercase C. And Dalton has that already set up correctly if you go back to his post at time 12:19. I was just a little too stubborn to keep using P and Q. Alright, so Danny typed, so in 256 coin flips, the chances of getting one head is B. Of getting exactly one head, yes, that is correct. If a head is representing having a bit transmitted incorrectly, then yes, that would be the answer. That would not be correct. Exactly. So dividing the 0.3072 by 256 does not solve for P. That is correct. So Nathan is correct about that assessment. Yep, that you can call it that. It's not so much it's reversed, it's really just looking, it's just seeing if you guys can make the connection. So in this one, I give you the actual probability, and you have to use what is given to you to reverse and get back to the per bit error. Yep. So that'll be me standing upside down to do my hair splitting. Wait, that's inversion. Inversion and reversing are different since we're in hair splitting mode. So I have to be walking backwards and while I'm hair splitting, not standing upside down, because that's just inverting and not reversing. And I think I gave you guys a bulleted list of how many different types of probability stuff that we have talked about and how to differentiate between those. I think that was talked about on one particular day, and it was in a form like this, in a note type of form. All right. So then in part 2, we're trying to figure out the chances of having 2 or less heads. Yep, but you have to remember to subtract that from 1, because it is the chances of having too many error bits for self-correction that we are interested in. That's what the question is asking. So using C, compute the chances of a packet having too many error bits for the self-correction mechanism. So we're interested in 1 minus the chances of having 0 to 3 error bits. All right. So both of these formats are correct, okay? Because this one, start the summation from 4 all the way up to 256. This one is going to give you exactly the same answer. It's just that if you are solving this empirically or using actual numbers, this one is a whole lot easier to compute unless you basically write a script, as a part of answering the question. Because these two terms are complementary of each other, they add up to 1. So this sigma notation and this sigma notation, without the 1 minus obviously, they add up to 1. Because they add up to this amount, and that amount always adds up to 1, because P and Q add up to exactly 1. And 1 to the power of 256 is 1. Yep, there we go. All right, we got a few more people typing, and we'll get those questions answered. Or not. I saw a few people typing, but I did not get anything in the text channel. All right. All right, so it looks like we are ready to move on to another question. Is that correct? I mean, if anyone wants to stay with this question, I'm good. I'm good with that, and I just want to make sure that we are ready to go. Okay, so all right, so let's move on to. I'm gonna leave question number two behind a little bit because we're gonna talk about the solution of the Dijkstra's algorithm. I think that's due today, and I could be wrong about that, but I think that's due today. So I'll confirm that later on. Since we are talking about probability, let's move on to question number three, which is a fun one too. And this is the one where the key was originally incorrect because I wrote the wrong script. Okay, I put a bug into the script and it was quoting the wrong number. And then I looked at the script itself; it was actually correct. So I ran it again and it gave me the right answer. So I must have uploaded the key before I fixed the bug, and then I forgot to re-upload the generated answers after that. Oh, it's due on Wednesday? Today is Dijkstra's. Okay, so I think this is based on Dijkstra's. No, this one is based on the A star algorithm, so I can't really talk about that one. Yeah, let's talk about this one on Wednesday because I think it's better that way. And today we'll talk about the solution of the homework related to Dijkstra's algorithm. So that's what we're going to do. I'm just looking at the time. I think we got enough time to do it. All right, so let's take a look at question number three. And I'm going to read the question as I read, we'll see whether it is confusing or not. So a team-based video game requires G equals to 5 players on each team. A tournament organization put together a group of 10 people, and I give each one a variable name, so this way you can quote those variable names as you try to work out the equations. Two teams are formed by randomly assigning members of this group of players to each team. Okay, so let's refer to the teams as Team E and Team F. So there are two teams. Note that this process only takes care of team membership. This process does not dictate who should play which role in a team. A team manages its own role assignment after membership is determined. Alright, so far what we know is there are 10 people, there are 10 players. There are two teams, each team has 5 people, and then we have some kind of a random process to assign players to the two teams. Unfortunately, x equals to 3 people out of the 10 players are salty. Okay, so if you're not familiar with the term, what is a salty player in especially a team-based video game, that's okay. All that means is these people are impolite, rude, easily triggered, and so on. They make it not fun for the rest of the team and even the opposing team. Okay, so first figure out K, the cardinality of omega, the set of all possible outcomes. Be sure to explain your rationale of how you formulate the expression. Alright, so now we have to get back into the mode of trying to map this particular problem in the exam to things that we have already solved. Okay, so we have to first ask the question, what is a trial? Okay, what is the experiment? What is a trial? And how do we map these things? So there are several ways to look at this, okay, because I did not quite say, what the process is. All I said is randomly assigned, right? So one way to look at this is to say, okay, we'll just, randomly pick 5 people into team E, and then whoever is left is in team F. That's one way to look at it, which is consistent with the description of randomly assigning members of this group of players to each team. Does that make sense? Because I want to first make sure that that part is okay. If we randomly pick 5 people into one team, it is equivalent to randomly picking members for both teams, because whoever is left has to go to the other team. Okay, very good. So we have a confirmation that we have a yes here, and that alone is enough to figure out K, because we have basically 10 people, of which we choose 5 to get to to go to team E, and whoever is left is automatically team F. So the first part of the question is 10 choose 5. And if you would like me, I can type it here. Okay. All right, so the first thing I will do is I'm going to nest the bullet points. So let me add a indentation to all of the lines. So this way it's indented. Everything is indented for Q1. And now we can have Q2. So it's just easier to Q3, sorry. So we can have Q3. The first part is going to be 10, choose 5. All right, so there are 10 choose 5 ways to assign the 10 people that we have to the 2 teams, each team having exactly 5 people. All right, so let's read the next part of the question. Oh, before we go, okay, so let me show you, why, how we can map this question to combination. So the first thing we notice is what is each trial? Each trial is basically, okay, we're picking a person and say, okay, this person is going to team E. We'll choose 5 people for team E, and then whoever is left, goes to team F. So the next question is does it have replacement or not? Well, since each player, after choosing each player to be on team F, that player cannot be chosen again. So it is without replacement. So now that we know it is a without replacement kind of deal, the next question is it a combination or is it a permutation? In the case of a combination, the ordering is not important. So if you want to pick Vlad first and then Ishan next and so on, versus picking Ishan first and then Vlad next, it doesn't make a difference, okay? And that is part of the reason why I mentioned very specifically that the role of what each person does in a team is up to the team itself to decide. Okay, so that is basically me trying to make sure that people do not assume and say, okay, whoever is chosen first, has to play this role. Whoever is chosen second has to play that role, and so on. So that has nothing to do with it. Okay, so that is without replacement, and ordering is not important. So we now know that we are dealing with a combination kind of problem. So the next question, once you know it's a combination problem, the next question is how many are we choosing from and how many are we picking out of that? So since we have 10 people to start with, so it kind of makes sense. 10 is where we want to start. So 10 would be how many we're choosing from. And since each team has only 5 people, so 5 becomes the next number. So that's why we have 5 as the number of people that we are choosing out of 10. All right. So is that okay? I mean, I'm just trying to explain how to look at this problem and then map this problem to the concepts that we have already talked about. All right. All right, so that's the first part, and the answer is 10, choose 5. So let me give it the correct symbol, which is K. All right, so there we go. All right. All right, back to the question for part number 2. So for the second part, we want to figure out L, the number of ways that Team E can end up with at least 2 salty players. So this is where the script, that I originally, it's the script that I used to generate the answer, had a bug and it, gave the wrong number. All right, so let's look at this and figure out, how do we figure out this number L here. The first thing we want to know is the Team E can end up with at least 2 salty players. So from the perspective of looking at the event, okay, remember the event is basically a subset of all the possible outcomes. And so the event is basically, in this case, is asking, all right, so what are the chances that Team E can end up with 2 salty players, and also will end up with 3 salty players? Because there are exactly 3 salty people within the 10 people. So 2 is possible in a team, and then 3 is also possible in a team. All right. So now we look at this and we ask, how do we solve this problem? And how does it map to things that we have solved already in this class? So the first thing that came to my mind, okay, and some people may say it's not fair because you came up with these questions to begin with. Well, that's actually not the case. Okay, so when I came up with these questions, I don't really have a formed solution, and then I would actually try to solve the problem and then figure out, oh, okay, so it does map to that. So it maps to the lotto problem. Okay, it maps to the lotto problem because of the 5 people in a team. There are, okay, we'll focus on one subproblem at a time. Okay, so let's just focus on the problem where we have exactly 2 salty players out of the 5. Okay, so now the question is, how many ways can we end up with exactly 2 salty players? Well, we have 7 people within the 10 people total who are not salty. And then we have exactly 3 people who are indeed salty. So if you think about the lotto problem, after a lotto draw, we have exactly 5 winning numbers, and then we have what, 69 minus 5, which is 64 non-winning numbers, right? So out of the 69 possibilities, out of the 69 possible outcomes, for the first trial, we now group them into 2 subcategories. One is a winning number, there are only 5 of those, and then the other 64 are non-winning numbers. So if you want to get, I cannot remember, I think it's a $2 prize, where you have to match 3 of the winning numbers and 2 of the non-winning numbers. I cannot remember exactly, but the point is, in that case, you have 5 choose 3 ways to get 3 of the winning numbers, and then you have 64 choose 2 for the 2 non-winning numbers, and those 2 need to be multiplied to give you the total number of ways of getting all 5 numbers on the lotto ticket. And the reason why it is multiplied is basically for each way you choose 3 out of the 5 lucky winning numbers, there are 64 choose 2 ways to choose the non-winning numbers. So the key here is for each, okay? Because if I say for each one of these, we basically have a tree that fans out in a certain way. Then when you want to count the total number of leaf nodes, then you have to multiply the fan out from the first part of the tree to the fan out of the second part of the tree. So you have to multiply the 2 fan out ratios in order to figure out the number of leaf nodes in a tree. So it's the same thing over here. Okay, it's the same thing over here, except the values are different. So in this case, for the case where we want to have exactly 2 salty players, then we have to look at it as 7 non-salty people choose 3 of those, and then of the 3 salty players, choose 2 of those. So that will give us the exact number of having exactly 2 salty players in Team E. And then when you shift the numbers by 1, then you will end up with the value of the number of people, the number of ways to choose 2 non-salty players and then 3 salty players. So this is variable L, and I am going to give you the equation here. Alright, so L equals to, let me make it a new point, because it is for the second part of the question. There we go. Alright, so this becomes 7 choose 3. I don't need parentheses around this. Get rid of the parentheses. Times 3 choose 2. And it doesn't like my formatting for some reason. What did I do? Oh, I see. Wrong type of parentheses. Thank you. Thank you, Nathan. Um, I'm not sure. I'll try to address that later. Okay, that's referring to Danny's question. All right, so that's the first portion. This is the first portion where it addresses the number of ways to end up with only exactly 2 salty players. And then the second part is to end up with exactly 3 salty players. So let me get this done first, and then I'll go ahead and address Danny's question. There we go. Okay, so that's basically the number for L. And the format should remind you of the lotto problem, okay, which is the problem that I gave you guys before the practice. I shouldn't say that. Okay, stop. Okay, before I gave you the exam from the fall of 2021, because the one before that, had the coin flip problem and also the lotto problem. So this is the lotto problem. So are we okay with this? YL, the variable L, is the summation between these two. And I can hear those questions. Even though some of you are not asking, I can hear those questions in your mind of saying, so when do we use add? When do we use addition? And when do we use multiplication? So I kind of explain why we use multiplication here, because it is saying for each way of choosing 3 out of 7 non-salty players, there are 3 choose 2 ways to choose the salty players. So when do we use the plus? When do we use addition? Okay. The first term here, the first product, is referring to the number of ways to choose exactly 2 salty players in Team E. And then the second product is referring to the number of ways to choose exactly 3 salty players for Team E. So when you add these two together, it becomes the number of ways to have at least 2 salty players in Team E. Sure. So the question, but however, I have this question because I could hear that in your mind, or some of you, is why are we adding here instead of multiplying? So the multiplying has to do with, for each node of the tree, it fans out to this many things, and that's when we use multiplication. This addition here is basically saying, look at this bunch of leaf nodes, okay, in the tree, and look at these bunch of leaf nodes in the tree. In other words, the leaf nodes corresponding to the first product and the leaf nodes corresponding to the second product, they do not share an ancestor except for the root of the tree. So if we are interested in both of these particular subsets and say, well, both of these are important because I really don't want to play in a team with at least 2 salty players, because that's that's a lot of salty players in the team. Okay, having 2 people who are salty, who can basically talk, and they can bounce off the negative energy from each other, to the point where the rest of the team cannot function. Okay, so that's why 2 or more, is bad. Okay, having 1 is not good, but having 2 or more is just asking for trouble. Now, having 3 is entertaining, because I have seen some of my kids, game where they have like 3 salty players in the team. It's like, wow, you should just kind of log that conversation, because that's kind of entertaining in a bad way. Okay, so that's why, so getting back to this point here, multiplication is, when you say for each node it has this fan out, then we use multiplication. When you use addition, is when you look at the actual leaf nodes and say, this bunch of leaf nodes, we want to include it in our count. But look at those bunch of leaf nodes too. We want to include those in our count as well. That's when you use addition, because we are just trying to count the number of leaf nodes of interest to us. So I hope this kind of helped to explain, when to use multiplication and when to use addition. All right. And so if you guys have questions about that, go ahead and put it into the text channel. And then the last one is third, compute the probability that team E ends up with at least 2 salty players. Well, that would be pretty easy to do, because we just have to look at the 2 numbers that we have already figured out. K is the cardinality of omega. And if someone is asking, so what is omega in this context? Well, that means someone has not been getting familiarized with the terms. Omega in this context is referring to the set of all possible outcomes. Okay, if you have 10 people, 2 teams, each team can have up to 5 people. There are exactly 10 choose 5 ways to assign team members in a random way. Then what about L? Well, L is the cardinality of the event set. Okay, so event is basically a subset of omega. It is representing elements that are of interest to us. So what is of interest to us is a team, team E, ending up with 2 or more salty players. So L is the count of the number of ways by which team E can end up with 2 or more salty players. So now we have everything set up already, because the probability is the cardinality of the event divided by the cardinality of omega. So to answer the question of the third question, let me see what symbol I was using. E. Oh, okay, it doesn't actually have a symbol. So I can just go ahead and... Oh, I just got out of the editor. Let me get back in. Nope, it doesn't like that. Nope, I'm not out. All right. So let me get back to... Oh, we are looking at it. Okay, never mind. Okay, that's me confusing myself, like really badly. Because I was looking right at the tab of my notes, and I was trying to find it when I'm looking at it. All right, so the answer to the third one is basically just L divided by K. So that would be the answer. And in this particular case, you can use any spreadsheet. That will give you. I mean, if you use Excel or use Google Sheet, they can all compute combination for you. So this one, you can get to the actual numerical answer pretty easily. And I think most calculators have combinations and permutations as well. All right. So are we good with question number 3? If you have any questions about question number 3, please ask those questions now. And I'm getting ready for question number 4. Yeah, so for question number 3, it did not say that I just want the formulation. So it does expect you to give me the correct value in this case. But I can also tell you that if you give me the formulation, in other words, if you just give me this because you ran out of time to actually start the spreadsheet to do the calculation, you get at least a B out of the 4 if you explain it. Now, this does not actually have explanation. Okay, I have to point that out. So the way the answer that I put out in question number 3 did not include the rationale of why I use these specific format. Okay, so that part was basically spoken. I was using words to describe how I evaluated the question and how I decided this is about combination, this is without replacement, and that's why we use the combination, the equation here, and why I chose 10 on the top and why I chose 5 at the bottom. So all of those were explained, but I didn't type it out. Okay, so you guys will have to also explain your rationale as you figure out, oh, okay, I think it is this, and this is how we formulate it. All right, so I just want to make it extra clear that this is not acceptable as a final answer. This is just me typing out the final answer, when I was verbally explaining the rationale that led to the formulation of these three equations. Well, the third one is not technically an equation, the expression. There we go. All right. Basically, in the final exam, just type out what you are thinking. Okay, basically you look at this question and it reminds you of this, and or just explain in your mind, how you make the connection to the concepts that we have talked about in class, and how you apply, the concepts that we have learned in class to solve the problem in the exam. Yep, I like that, Sebastian. That's a good one. So what Sebastian put into the text channel is to look at the outcomes as a tree. Now, in this case, it is a tree of permutation. So I do have to point out that this is not a combination thing; it is a permutation thing, because having a head and then a head versus having let me take that back. Having a head first and then a tail versus having a tail first and a head, those are considered two different leaf nodes, because you can see how. Okay, let me see if I can bring this into the window that you can see. Give me a second here. There we go. Okay, so you can see how there are two leaf nodes that would have been combined into one single combination, meaning this guy and this guy over here. In order to get here, we have to first land on the head and then we land on the tail. In order to end up here, we have to first land on the tail and then we land on the head. So when you look at these four leaf nodes, each one is representing a permutation, okay, not a combination. On the other hand, the binomial theorem, the coefficient, is about how we can find a bunch of leaf nodes and say, these guys, even though the permutations are all different, they all end up with exactly the same value when it comes down to the probability. So instead of doing the addition a bazillion ways, a bazillion times, why don't we just add a multiplier and say this is and choose I and be done with it? That is why we see the combination in the binomial theorem, because we are basically saying, this guy over here and these leaf node over here, as far as I'm concerned, they are the same thing. Okay, because I'm only concerned about the number of heads versus the number of tails. I don't really care about the ordering of when how it happens. So then we are basically looking at this leaf node and looking at this leaf node here and say they belong to the same group. Okay, because we don't care about the order. So now it becomes a problem of counting the number of leaf nodes of this particular nature. And in this very specific case, the nature is there's exactly one head and there's exactly one tail. Okay, I don't care about the ordering. I just need to make sure there's one head and one tail, and both of these satisfy that requirement. And that is also why in this particular case, the coefficient of this probability is going to be 2 choose 1. Okay. So I do want to point that out because this is a tree that represents where each leaf node is representing a permutation. And I'm also trying to explain to you, how we look at permutation and say, okay, all of these permutations really belong to the same combination. So that's why we have the coefficient itself to take care of, the counting of equivalent leaf nodes, even though each one is a permutation that's different, but they all belong to the same combination. All right, so I'm not sure whether that helps or not, but that's my explanation, okay, to kind of clarify and point out, what that tree is about, that Sebastian just posted. But that's a good example. I think a better way to, if you expand the tree, so for those of you who really want to do some more work, just so that it will help you understand, what each leaf node is representing. Expand that tree to have 3 coin flips. Okay, so you end up with 8 leaf nodes. So of the 8 leaf nodes, okay, each one is representing a permutation. So look at those 8 leaf nodes and figure out what 4 combinations are corresponding, what those are corresponding to in terms of combination. There are 4 combinations corresponding to those 8 leaf nodes when you expand that tree to have 3 trials instead of 2. Okay, so I encourage you to work on this, by yourself. Okay, because it's more of a mental exercise than it's actually a complicated, or tedious kind of thing to do. It's really just one way for you to kind of visualize and understand, how permutation and combination relate to each other, and how we come up with the coefficient right here. Okay, and in a much more pictorial way. So that's my recommendation to you. All right, so we are down to the last question, which I think we might have addressed already. All right, so this is the one where there are some questions. So we'll go ahead and take a look at this one. So what is the total number of possible different tickets? So let me first read the overall question. In a specific Powerball Lotto draw, which means this is after the winning numbers are drawn as well as the Powerball number, there are 4,447 tickets matching 3 of the lucky numbers and do not match the Powerball number. So I'm giving you the exact number of one particular Lotto draw, of the number of tickets that win a very specific prize. Okay, 3 of the lucky numbers and not the Powerball number. And here's a link to the Lotto web page itself, which is not really needed, but I just put it here just in case people want to refer to it. The first part of the question is, what is the total number of possible not sold different tickets? So basically I'm asking about, so what are the total number of possible tickets that are unique? I know you can look it up. You need to supply your rationale and derivation of this value to show that you understand how to formulate the value. Okay, now this is really important to understand that this is what I am really looking for, because if you follow this link here, you would find the actual value. So I'm not interested in the actual value. I'm interested in how do you formulate your expression so that it evaluates to the actual value. All right. So in this case, we have 3 of the lucky numbers out of 5, right? So we have 5, choose 3 as one of the numbers. And then the other two numbers on the ticket, they have to match 2 of the non-winning numbers. Okay, so we have 64 of the non-winning numbers. So you have to subtract, so you have to compute 64, choose 2, and then multiply those 2 together. Once again, why are we multiplying? We are multiplying because for each way of choosing 3 of the 5 lucky or winning numbers, there are 64 choose 2 ways to choose the non-winning numbers. Okay, that is why we multiply. And in this case, because the Powerball number is not matching, so there are 25 ways for the Powerball number on the ticket not to match the actual Powerball number, because the Powerball number is 1 out of 26, right? So there's one way to match it, 25 ways not to match it. So the total number in this case is going to be 5 choose 3 times 64 choose 2 times 25. Okay, so you have to remember the 25 because the 25 comes from the 25 ways of not matching the Powerball number. That would be n. Next is given the number of matches of the lucky numbers and whether the Powerball number is a match or not. What is Q? The total number of different possible tickets. Again, this value can be looked up, so show your rationale, explanation, and derivation in this answer. Alright, so given the number of matches of the lucky numbers and whether the Powerball number is a match or not, so the total number of different possible tickets. So now you have to figure out what is Q, the total number of different possible tickets. So this one is really just the general lotto problem where you have 69 numbers of which you choose 5, and then you have 26 numbers for the Powerball number where you choose 1. So that becomes the number for Q. So once again, Q is 69 choose 5 times 26 choose 1. So I know someone is going to say, well, but isn't that just 26? Because 26 choose 1 is just 26. The answer is yes. Okay, it is just 26. But you can always cast that number back into the way we look at combinations, which I think is a better way to do it. Since we want to be aware of how we are choosing combinations, how we are computing the number of combinations. So even though in that case is a degenerated case where you can just say 26, if you just say 26, I'm not going to take any points off. But I do want to point out that 26 is coming from 26 choose 1. Alright, so here's the third one. The third part of the question is assuming M is representative. So M is this number here, is representative based on the actual number of tickets actually issued. Compute Q. Again, this is me making a mistake, using Q as a variable again. And the key does reflect that. I said this is oopsie. The projected number of the number of tickets actually sold. So the way you answer this question is you basically look at the ratio of n divided by q, and you say based on that ratio, 4,447 divided by the actual number of tickets sold should be about the same. So once again, n divided by q equals to, or approximately equals to, m divided by whatever amount you're supposed to find out here. So once you work out the algebra, that number is going to be 4,447 times q divided by n. That would be the answer of the third part of the question. So once again, in this case, it only involves combination, and you can use a spreadsheet easily to find out combination, and most calculators can do combinations as well. So in this case, a numerical answer is expected. So that's case 1, and the only difference between case 1 and case 2 is case 2 does require the Powerball number to be matched. And the number of lucky numbers may not be exactly 3, but basically the main difference is case 2 requires the Powerball number to match. So in that case, the total number of tickets winning this particular prize would be, in this case, 5 choose 3, which is the number of ways to choose 3 of the 5 lucky numbers, times 64 choose 2, which is the number of ways to choose 2 of the non-winning numbers, times 1. Okay, because in this case you want to match the Powerball number, and that's why it is a 1 following that. So that would be the answer of the second part. And then the third part is computed basically the same way, because we have the same queue anyway, because this queue is referring to the same queue over here, because the total number of possible tickets, possible unique tickets, doesn't change, so it's going to be the same queue. So in this case, the answer is going to be 177 times q, and then divided by the answer to the first part of the question. And let me see, I think the question might have been formulated incorrectly. Let me just take a look here. Given the number of matches, what is Q? The total number of different possible tickets. Oh, okay, so I was using the same. Okay, this Q is incorrect because I'm using the same Q over here. This Q. All right, so this Q over here is what is n, but the way you use the ratio is the same. All right. Well, does that answer the question? I can type it up in the text in my notes too. All right. The key that I distributed last Wednesday actually has an answer to this question too, so you can refer to that one also. So if you go back to 0504 and go all the way to the end, okay, I'm just clicking on it right now. That should contain the answer to all 4 questions. Now remember, one of the questions I have not addressed, and I got 5 minutes to show you the answer to the Dijkstra's algorithm example. So this one, this is it's an automatically generated answer, but it does give you the rationale of how to reason things out, so you can study that. So now let me go back to the last thing that we need to do today, which is to look at the problem that we have for the assignment, and then go ahead and do that. And I have to find my tab for Canvas, which is somewhere. I have to locate it, or I thought it's somewhere here. All right. Too many tabs. All right, let's go there. All right. And I'm going to put it into the Google Sheet that's linked from the assignment. You might want to open up the assignment just so that you can refer to the problem itself. And I am going to work on the spreadsheet. So if you open up the spreadsheet, I'm going to work on that one. Actually, I will put it over here. So I'll open a new tab for the solution of the homework for this semester. So solution of spring 2022. And the format is going to be very similar. So I'm going to copy and paste all the columns to the key of this semester. And then we'll go ahead and read the question. Alright, so this is what I'm going to do. I will peel the question or the assignment off so that you guys can refer to it on the side too. And then I'll work on the solution in the spreadsheet. There we go. Alright. Alright. So the first thing is we have 5 vertices instead of 4 this time. So we're going to have to extend our L values to also include L of E. And then the second thing is the destination is no longer D, because this time we have 2 destinations. We have D and C as our destinations. So we're going to unboldface this, and then boldface this guy, and boldface this guy. Now, if you don't boldface C and E, it's not a problem. Okay, I will not take any points off if you do not boldface C or E. I do that just so that I can easily tell which 2 are the destinations. Because in the initialization, it makes a difference. The destinations L values are always zeros because they are 0 away from a destination, and then everybody else is going to have an infinite value for the L value, because before we explore, it is very possible that these vertices are not reachable. The set of Q is initialized with all the destination vertices, which would be C and E, and then E prime is initialized to be an empty set. So that's the initial condition. Row 2 is representing the initial condition before we get into the while loop. When we get into the while loop, the first thing we do is to find out from the vertices inside Q which one is, or which ones look the most promising. Well, in this case, they're both equally promising, so I'm going to pick E first. Okay, I know most of you pick C. That's okay. You can pick either one first. It doesn't really matter. But I'm going to pick E first. Okay, so I'm going to say E. Vertex V is vertex E. And then we have to look at all the incoming vertices to vertex E. But after I pick out vertex E, I have to remember to remove E from the set Q. And now we have to look at all the incoming edges to vertex E. There's only one. I believe it's AE with a cost of 6. So this becomes A. So when we look at the sum of L of E and the distance of the edge AE, which is 6, 0 plus 6 is 6, and we ask, did we find a better way from vertex A to a destination? The answer is yes. Okay, so I'm going to put a 6 here because that is the length of the shortest path from vertex A to vertex Z. So the E prime is now going to contain that particular edge, which is from A to E. And I also have to remember to add vertex A to the set Q, because now the L value of vertex A has just changed. And that's it for the for each loop, because there's only one incoming edge into vertex E. And now I'm back to the while loop. Looking at the set Q, we have 2 vertices A and C. The L value of A is 6. The L value of C is 0. So I'm going to choose C. So C is going to be our V, and we remove C from set Q. And now we have to look at all the incoming vertices, all the incoming edges to vertex C. There are quite a few. There's BC, there is AC, and then there's also DC. And the way you explore these edges, the ordering does not matter. So I can look at DC first. So if I look at DC, I'm adding the distance of the edge DC to the L value of C, which is 0. The edge DC has a distance of 1. 1 plus 0 is 1. And I'm comparing that to the L value of D, which is infinity. So 1 is less than infinity. Put a 1 here. There are no outgoing edges from D, so it's not going to impact anything I have at this point, but I do have to remember to add DC as an edge into E prime, and then I have to remember to add D to the set Q. There we go. Now we look at another incoming edge to vertex C. Let's see which one I should pick here. I'm going to look at B. Okay, BC. So now we look at BC, the distance of BC, which is 2, plus the L value of C, which is 0. 2 plus 0 is a 2, but we are comparing 2 to infinity. 2 is less than infinity. So now we have to update the L value and add the edge BC into the set of E prime. So we have AE, DC, BC in the set of E prime. And we also have to add B into the set of Q because we just changed the L value of vertex B. And now we look at the third edge going into vertex C, and that would be AC. So now we look at vertex AC. AC has a distance of 5. L value of C is 0. 5 plus 0 is just 5. And we are comparing 5 to the current L value of A. 5 is less than 6. So we have to update a bunch of stuff. And this time we do have to take out the edge AE first before we add the edge AC back into the set of E prime. And then we have to add vertex A into the set Q. But A is already in it, which is fine. We just basically say, okay, we don't have to make any actual changes to to the set Q. So that should conclude the second while iteration, all the 4 of the second while iteration. So now we have 3 vertices in the set Q, and we have to look for the one that has the least L value. And A has an L value of 5, B has an L value of 2, and then D has an L value of 1. So the choice is pretty simple. I think vertex D is the one that we want to choose to explore. So now we take D out of the set Q. So it would have A and B left. And then we look at the incoming edges to vertex D. There's an edge AD, and that's it. Okay, so there we go. The edge AD has a distance of 1, and let me see. Trying to yep. So the L value of D is 1. The edge AD has I take it back. A distance of 5. 5 plus 1 is 6. So let me see if we found a shorter path from vertex A to a destination. What we found at this point has a length of 5 already. So the new path has a length of 6. We did not find a shorter path. So we did not end up changing anything. So now we get back to the while loop. The while loop now has A and B in it. We find the one with the shorter length to a destination. So that would be B this time. So L of B is 2. So we're going to choose B as our V. And then take that out of the set Q. And then now we look at all the incoming edges of B. Let's see, we have AB, and that's it. Okay, so there's only one incoming edge. So now we look at the edge AB, which has a distance of 2. And we look at L of B, which is also 2. 2 plus 2 is 4, which means we just found a path with a length of 4 to go from vertex B to a destination, to go from vertex A to a destination vertex. That is indeed shorter than what we have found so far, so we have to do some updates. So L of A is now updated to a 4. We go into E prime, we take out AC this time, replace it with AB, DC, and then BC. Did I forget something? Yes, I think I mentioned that you can indeed start with either one. I know I think I even mentioned that most of you probably started with vertex C because that's what most people do. Follow the alphabetical order. In which case, your trace is going to look a little bit different from this one. So I'm only looking for consistency. You could have chosen to start with B or C or E. Yes, that was mentioned. All right, so since we just updated the value of vertex A, we have to add vertex A back into Q. Okay, so even though it's already there, it's technically we still have to put an entry in column A, and that would conclude all the four iterations, because vertex B only has one incoming edge. So for the next while loop, we're gonna have to take the only vertex out of Q, which is vertex A, and now Q is empty. And vertex A has no incoming edges. If you go through the E or D, you will find that A has no incoming edges, and that's it. Okay, so there are no for loop after this, and that concludes everything. So E prime should look like AB, DC, BC. And someone may be asking, what about E? Well, E does not need an edge to get to a destination vertex, because it is a destination vertex itself. So that's why you don't see an edge leading from vertex E to anything. All right. So let me see what other questions you guys have. After we have chosen E or C, it is important to choose the least one next. Well, okay, so let's go back to the algorithm, okay, because I think it really boils down to how to read the algorithm, and I think that is important. So, and for those of you who think you understand everything already, that's fine, not a problem. You can sign off. It's still getting recorded, so if you change your mind and you want to go back and look at, watch the video again, you can always do that. This is why I do recording. There we go. Okay, so I am putting the algorithm back into this page. All right, so the question is, how do we read the first statement after the while loop? Select V in Q such that W in Q, L of V is less than L of W, and so on. So if you have multiple candidates, this statement does not specify which one you need to choose first. Okay, so you just have to choose whatever you choose as vertex V has to meet this requirement. If there are multiple ones that can meet this requirement, just pick any one of those. So, so the short answer to Daria's question. Okay, so Daria has two questions basically. Daria's first question is, after we have chosen E or C, it is important to choose the least one next. So I'm going to assume the least in this case is referring to the L value. I'm not sure. But the second question seems to clarify the first one. I mean the order of W going to be DBA. Nope, it doesn't matter. So if you look at the for loop here, the for loop is simply saying, okay, give me an edge, okay, for every edge of this particular subset, pick one and then do the following. So once again, the ordering is not important. As long as you get every single element of this particular ad hoc set, you're good. So ordering is not important in that case. All right. Okay, so you still have the A-star algorithm that is due on Wednesday, and there's also the one question left in the exam from last semester, which relates to the A-star algorithm. So that's why I defer the discussion of that particular question until Wednesday, because I want to talk about the solution to your A-star homework first. And then, in the same context, then we can start to talk about the question in the final exam of last semester. All right. So any other questions? Yeah, I know we overran by 12 minutes or so. But since you guys are supposed to spend, what, 10, 15, cannot remember. Not 15 hours. I think it's 10. Nope. It's a little more than that. I cannot remember the number of hours you're supposed to spend on this class. Just consider this extra time that we do the synchronous lecture as part of that time. then we're all good, right? Oh, Nathan's typing something. All right, so this is the graph that I use to visualize the input output. All right, let me take a look at that. Because I'm using a dark theme on Discord, and Nathan is probably using transparency, because that's what we're supposed to be using for for the background is transparent. So it makes it kind of hard for me to see the graph. Okay, now it shows a lot better because I'm opening it in Firefox. Okay, so let's take a look. Yep. So this is the starting. This is the starting point, which is the complete graph as the um, question, and this is the solution graph, which means it only contains edges that will lead a vertex to the closest destination vertex. And that makes perfect sense, right? Because E and C do not need incoming edges. Oh, C is right here, sorry. So E and C do not need outgoing edges because they are destinations already. And D is going to C because that's the only destination it can ever get to. So there's not a question about that one. So from A's perspective, it is the interesting one because A has quite a few ways to get to a destination. It could have gotten to E, but that is actually not a short path. Even though it's a single edge, the length of the path is actually quite long. It could also go through D to get to C, but that's equally long compared to going from A to E. A can also go to C directly, but that is still long. And the shortest path from A's perspective turns out to be going to B first and then going to C. So this graph here as the solution graph is correct. And that's a good representation. Thank you for posting the solution graph in the text channel. Yay. All right, so I think we are done for today's lecture. If you guys have any questions, go ahead and post it in today's channel, or you can post it in the questions channel. Both will work for sure. And then focus on the A-star algorithm and also the question about the A-star algorithm in the exam from last semester. Because it's an interesting question, because I'm giving you a partial trace of the execution of the A-star algorithm, and I'm asking you to reverse and find certain things, about the original problem. Now, there are only so many things you can reverse to kind of figure out about the original problem, but I want you to think about this, okay? Because as you work on the algorithm, going quote unquote forward, to use Danny's terminology, what can you use as clues from the trace of the algorithm to go backward, to reverse the whole thing and know certain traits about the original problem itself. That's basically what that question is about, is to basically go backwards, okay, to figure out what the original problem might look like. So that's it for today's lecture. We are down to one lecture left on Wednesday, and then we'll have our final exam. I cannot remember the date, but I think I wrote it down somewhere. I think I put it on the calendar of the class. So let me check. Pretty sure I put it into the calendar. Let me see. View calendar. I'm pretty sure that question has been asked and answered multiple times. And I did not put it into the calendar. I have not done that. Okay. So it is May 16th. Thank you, Nathan. It is May 16th. I'm going to add it to the calendar so this way I don't forget and we don't forget. All right, cool. Looks like we don't have any additional questions. I will see you guys on Wednesday, and try your best to work on that question as you work on the A-star algorithm, because I think that will help deepen your understanding of the A-star algorithm. But more importantly, you learn about how to apply logic in a way that will help you in your career to find bugs. Okay, and I'll explain why that is related on Wednesday. All right, well, you guys have a good day, and I will see you on Wednesday, even though I don't turn on the webcam today. All right, bye.